In our last video, we talked about isentropic processes. This is going to be an example for that. Here we've got argon. It's going to be in a piston cylinder assembly. It's being compressed isentropically from state 1. Gives us the pressure, which is 150 kilopascal, and the original temperature is 35 degrees Celsius. Then we're going to go to state 2, where the pressure is going to be 300 kilopascal. We're going to assume the ideal gas model with a K value of 1.67. We want to find T2, and we want to find the work in kilojoules per kilogram of argon. Alright, so that's what we are looking for. Notice we have isentropic, we've got ideal gas. Those are keywords there. And I'm going to go ahead and write out our conditions. At state 1, we've got a pressure of 150 kilopascal, and T1 is going to be 35 degrees Celsius. State 2, we've got P2 equals 300 kilopascal. T2, we don't know what that is. We're looking for that. Now, we've got isentropic flow. K is constant. So let's figure out what equations we can use with that. So with that, since K is constant, we're going to have the equation T2 over T1 equals P2 over P1. The exponent's going to be K minus 1 over K. So this relationship here, it's got our pressures, it's got our temperatures. We know everything in this equation except for T2. So that's a good choice for an equation. So let's go ahead and plug in our numbers. We're going to have T2 over T1. This is 35. So we'll have 35. Now can we just leave that there? Nope. We got to convert to kelvins. So let's just add 273, switch it to kelvins. That's got to equal P2, which is 300 kilopascal, over the 150. And then our exponent. K is going to be 1.67, so we're going to have 1.67 minus 1 over 1.67. Now all you have to do is solve for T2. So T2 is 406.75 Kelvin. It wants the answer in Celsius, so convert back to Celsius and you get 133.7 degrees Celsius. That is T2. Alright. That was simple enough, right? Not too bad. Next thing, we want to find the work in kilograms, or not kilograms, in kilojoules per kilogram. Now think about what that's asking for. Work would just be in kilojoules. We want kilojoules per kilogram, so that means we want W over M. Alright. Now the easiest way to find this is going to be to use that old closed system energy balance equation. So let's start out with that. We got delta U plus delta KE plus delta PE equals Q minus W. These two go away. Now, what about Q? What's that going to be? We going to have anything there? We're not going to have anything there. Alright, remember this is isentropic. That means it's adiabatic. If it's adiabatic, Q goes to 0. So let's make a note on that so you know why that is. Okay. Now that we've got that, we just have delta U equals negative work. Now remember, this is capital U. We need to convert that over so we can use specific internal energy, because that's what's in the table. Multiply that by mass. That's going to equal negative work. We want W over M. We've got this M hanging out here. Let's divide through both sides by m. And then we'll get W over m. That's going to equal U1 minus U2. So now we've got that. All right, now you got a couple of choices here. You can go to the table, which that's what we usually do. But if you're using this textbook that I've got, if you go to the table, there is no table for argon in the ideal gas tables. So you're going to have to find something else to do. Now, what we're going to do, if you remember when we talked about ideal gas, we know that we can write internal energy at T2 minus the specific internal energy at T1. That's got to be equal to CV times T2 minus T1. All right. And we also know that CV is equal to R over K minus 1. So these were equations we've developed in the past. You just got to remember that we have them available to us. So we're going to be using this because we can't just go look up the argon data in the table because it's not there. Now, doing that, let's get back to this equation. So we're going to have W over M. And we're going to set it equal to CV times T2 minus T1 because we've got the temperatures. Now, let's replace CV with this. So that's going to give us R over K minus 1 times T2 minus T1. All right, now looking at that equation, did I write that correctly? Nope, I didn't. I'm just so used to, I was copying this from here, but if we look here, W over M is U1 minus U2. All right, notice this down here is U T2 minus U T1 equals this. So we need to flip these subscripts around. All right, so this one needs to be T1, this one needs to be T2. So make that correction. It's easy to screw up with all these subscripts we've got. All right. So now that we've got that, we can plug in our values. So W over M is going to be R. And for argon, we need to do R bar over the molecular weight. So we're going to have 8.314 over 39.94. Units are going to be kilojoules per kilogram Kelvin. We're going to put that over K minus 1. That's 1.67 minus 1. And then we're going to multiply T1 minus T2. T1 is 35 degrees Celsius. We can't just put that in here. That's got to be converted to Kelvin. So that'll be 308. And then we will subtract T2. T2 was the 406.75. That's already in kelvins. So now, do your unit check, works out, you end up with kilojoules per kilogram, that's what we wanted. So W over M is going to be negative 30.68 kilojoules per kilogram. It's negative, so that means work is done on the system. All right. So that's how you go about using those isentropic equations we developed. They can be quite helpful, so you really need to pay attention to those keywords in the problem statements. See you then.